Okay, thank you very much for the introduction and for inviting me. So this talk is based on a couple of papers with a bunch of people from the Quorum Institute, but especially with my former postdoc Gal Vardi and my PhD student Gilad Yehudai. Okay, so actually Misha gave a great introduction to many of the concepts I'm going to discuss in this talk, so I'll go for it relatively quickly. So, you know, when we talk about standard supervised machine learning, we assume that we have some kind of set of predictors H, we have some distribution. Our goal is to minimize the expected loss given some function over the examples. And the standard approach, of course, is to do empirical risk minimization. So we don't know the underlying distribution. Instead, we sample a training set and minimize the average loss over these examples. Now, in modern machine learning, you know, say in deep learning, usually we use very large predictors, which are over-parameterized in some sense. And this implies that usually we don't have like some single unique empirical risk minimizer, but we have many. And the question of which minimizer we get to depends on the algorithm that we use. And all of these minimizers have the same empirical risk, but of course not necessarily the same expected loss or other properties. Loosely speaking, we can refer to these properties as the algorithm's implicit bias. So the fact that we use a certain algorithm to perform empirical risk minimization biases ourselves towards certain solutions with certain properties. And classical learning theory, in some sense, you know, at least, you know, like distribution-free VC dimension type of theory, often doesn't distinguish between these different empirical risk minimizers. So, you know, basically, under certain conditions, you can learn with the empirical risk minimizer, and then any empirical risk minimizer is going to work. But here we're talking about situations where there are differences between the different empirical risk minimizers, and this raises all kinds of interesting and relatively new questions. So in this talk, I'm going to talk about implicit bias of training using gradient-based methods in three different contexts. One is in terms of generalization, when we hope to get a good predictor, and refers to the phenomenon of benign overfitting. Then we're going to switch gears and talk about privacy in the context of what implicit bias tells us for stuff like maintaining privacy or reconstructing data sets, and I'll explain more what this means later on. And finally, the issue of robustness, or more precisely non-robustness, to adversarial examples when you train, say, a neural network with gradient-based methods. Okay, so what's benign overfitting? So it's, again, it's very closely related to stuff that Misha talked about. So again, kind of the classical approach to explain learning with theorems, as I briefly mentioned previously, is that is like to identify situations where any ERM would work. So for example, the classical condition is when your class of predictors satisfies so-called uniform convergence. So it so happens, because the class is not too large or has certain properties, the average loss over the training set is close to loss uniformly over for any predictor in my class. In that case, empirical risk minimization would, of course, be a sensible thing to do, because it indirectly also minimizes the expected loss. And on the other hand, if you do have a gap between train and test performance, then, of course, you could get overfitting, and this appears in classical textbooks, such as this ones, or the ones that Misha showed in his talk. And when you have overfitting, at least in the worst case, you can have a bad predictor. Okay, if train error and test error don't align. So benign overfitting refers to this situation where you do overfit. There is a discrepancy between train and test performance. You get overfitting, yet somehow the learned predictor is still good. It still achieves good or even close to optimal performance. So I won't go over like the whole history of the development of this concept, but there was, first of all, there is a strong empirical evidence for this. I mean, this is something that is seen very often in deep learning and other learning models where you can essentially drive your train error down to 0 and still get good performance. And as Misha said, this actually goes back to way before deep learning. In the context of boosting, this was observed. And in the past few years, there's been an emerging understanding of when we might expect this behavior to occur, mostly for linear or kernel learning, for which theory is relatively tractable. So just to give a brief illustration, so you can take this classical one-dimensional fitting problem. Someone gives you data, you want to find the curve that fits this data. Good learning here will probably something like a straight line. So this would probably generalize pretty well on new examples, even though it does not perfectly fit the training example. And then there's this classical situation of overfitting, that if you do some high degree polynomial interpolation here, you would get something that gets 0 training error, but does not generalize well, probably. Benign overfitting refers to a situation where somehow, without necessarily meaning it, your training algorithm produces a curve which looks like this. So, this achieves 0 error on the training examples, but it also generalizes well, because unless you happen to hit points very, very close to your training examples, you would get something like the straight line, so you should be able to generalize. And actually, Misha showed a very similar thing in the context of kernel predictors, where for this type of problem, you do happen to get something similar to this. Okay, so the question, of course, is when can we expect this benign overfitting to occur? And of course, that depends both on the learning algorithm and the data distribution. So first of all, for concreteness, let's look at linear predictors, square loss. Now, if you use any kind of, okay, not any kind, but like vanilla gradient methods, say gradient descent to solve, or stochastic gradient descent to solve this ERM problem, driving the error down to 0, which we can assume that you can do because we're assuming that the dimension is much larger than the number of data points, then the gradient methods will converge among all possible interpolators, will converge to the one with the minimal norm. So benign overfitting in this setting refers to a situation where it so happens that this W hat, this min norm predictor, in terms of generalization performance, in terms of the expected squared loss, converges, the expected loss converges to the best possible expected squared loss among all linear predictors, as the dimension and the training examples goes to infinity. Now, there have been a couple of very nice works, for example, by Bartlett et al. From 2019, which actually characterized when can we expect benign overfitting to occur for linear regression with the squared loss. In particular, they showed that it happens if we're in the so-called well-specified or realizable setting, where y equals x times w star for some fixed w star plus noise. And moreover, the data distribution, distribution of x, it has a covariance matrix with many small positive eigenvalues. Now, I'm not going to quantify precisely what they meant here. Of course, they have like the rigorous statement in their paper. But roughly speaking, the intuition is as follows. So what they showed is that, in a sense, benign overfitting can occur if and only if the covariance matrix, the distribution of x, has something like the following structure. So that maybe after some rotation of the coordinate system, you can divide the coordinate of x into a relatively small number of significant or large coordinates. So think of this as k coordinates, where for simplicity, think of k as something fixed as d increases. And the rest of the coordinates are kind of small. Each one has a very small variance. So for example, you can think the prototypical case is when these coordinates, say, has some bounded spherically symmetric distribution, or like a Gaussian distribution. And what they were able to show is that if the dimension is sufficiently large, then the learned predictor, this min-norm predictor W hat, has the following structure. So the first k coordinates, the one that interact with the first k coordinates of x, basically gets a near optimal expected loss. Okay, so if you just use that component of the predictor, that would already give you a near optimal predictor. And the rest of the coordinates are just used to fit the training examples. On training examples, this is what allows you to get zero training error, but it has very little influence on new training examples. Because this is like in high dimensions, so on new examples, this component tends to be orthogonal to the relevant component of new training examples. So it really boils down to like this thing here. So like you have like a main signal that is near optimal, and then you have a sparse signal just to get the training error to zero, but it doesn't really affect your test performance. Okay, hence you can get this kind of benign overfitting for linear predictors in high dimensions. And most of the existing results for regression are kind of extensions of this intuition. But they tend to kind of focus on well-specified linear regression. So natural question is, what happens if we want to look at more general things, maybe not regression or not well-specified, or maybe even if we want a nonlinear model. What I'm going to talk about a little bit is some results for characterizing when benign overfitting can or cannot occur in more general settings. Okay, so it's still not, really deep neural networks or anything, but we can talk about agnostic linear regression, things like generalized linear models or single neurons, and also for classification rather than regression. Okay, so let's start with linear regression. So this is an agnostic case. So now I'm no longer assuming that y is x times w star plus noise. And roughly speaking, what we can show is the following. I won't have time to go into the proof details. If you're interested, feel free to talk to me later or look at the papers. So what we can show is that under appropriate assumptions, as the dimension of the number of training examples increase, the min-norm predictor that gradient methods converge to has the following structure. So the first k coordinates converge to this complicated looking expression. I'll explain more about it soon. And the other coordinates, whatever you get to, doesn't really affect your test performance. So the predictions of the min-norm predictor would be almost the same as if you just concentrated on the first k coordinates. Okay? So again, this is under the same kind of data distribution assumption that Bartlett et al. Showed that is actually necessary for benign overfitting to occur, even for well-specified linear regression. Okay, where you have like k significant coordinates and then many kind of small coordinates. Okay, so is this consistent? So, we want benign overfitting, we want this to be consistent, to converge to like the optimal linear predictor in terms of test performance. So generally, in our data model, for consistency, you would need the first k coordinates to converge to this expression. So this is like the optimal linear predictor with respect to the underlying distribution over the first k coordinates. Okay? So, is this equal to this? So actually, there are special cases where this is true. So for example, when we are talking about well-specified linear regression, both of these boil down to the first k coordinates W star, is the thing you would want to converge to. Also in some other special cases, like if the norm of your d minus k coordinates is a constant and you have some independence properties. But, in general, there is no reason to expect that this expression and this expression will be the same. And if they are not the same, you do not have consistency. You do not have a benign overfitting. So in some sense, benign overfitting in regression becomes very brittle once you move away from a well-specified setting. Moreover, you can show, based on this, building on this result, that benign overfitting actually doesn't occur in many other situations. So if you talk about generalized linear models or single neurons, you want to switch from the squared loss to absolute loss or some other regression loss, then even in a well-specified setting, you will not have benign overfitting in general. So again, I won't go into the proof ideas, but kind of the idea is that if you do perfect fitting in these models, you train to interpolation, you can translate this to doing perfect interpolation on certain agnostic linear regression models, and then plug in this result, and you get things which are generally not consistent, which are not the optimal thing that you would expect to get. Okay, that was about regression, where things look a little bit pessimistic. What about classification? Is that things are going to be relatively more favorable and more optimistic when we switch from regression to classification. So again, we're going to focus on linear predictors and binary classification, where of course our goal is to minimize misclassification error, probability that x transpose w times y is non-positive. And classification is kind of more robust in the sense that we don't really need to make x transpose w equal some real value y. We just need the sign to be correct. So how do we analyze this? So first we need to understand what gradient methods give us. So here again, luckily, people like Daniel Sudri and Markus Stilgarsky and others showed that if you train gradient methods with standard x-tail losses, say logistic loss, what you get to is what's known as the max margin predictor. So among all interpolating, zero error solutions, it's going to be the one with the minimal norm that achieves a margin of at least 1. Okay, so actually to be a bit more precise, the linear predictor you kind of go off to infinity, but in terms of the direction, which is what you care about for misclassification, you would converge to the max margin predictor. Now, several previous papers have studied benign overfitting for classification, but it's a little bit challenging, and the reason is that unlike the regression setting where the min norm predictor has a closed form solution, basically the inverse of the empirical covariance matrix times some vector, the max margin predictor doesn't have a closed form solution, which kind of makes it harder to analyze. So most of the previous papers kind of focus on specific setups where things are tractable, and actually often situations where the max margin predictor and the min norm predictor precisely coincide, and then you can use the closed form solution of the min norm predictor to analyze things. Okay. What we can show here, again, without going to the proof details, so also we cannot give an explicit expression for what the max margin predictor does, but we can say the following. So under assumptions kind of similar to the regression case, the max margin predictor, again, has this property that the last d minus k coordinates don't do anything. They're just used to fit the training data. They don't asymptotically have any kind of effect on the test performance. And on the first k coordinates, it turns out that w hat is asymptotically a minimizer of a certain weighted squared hinge loss function. Okay, so you basically take a hinge function, you square it, and you multiply it by this weighting that depends on the norm of the last d minus k coordinates of the input. And it's very important to notice here, so this is not related in any way to the training loss. So W hat, you use, say, the logistic loss to get it. But it turns out that implicitly, after you train it for long enough, your W hat is actually a minimizer of a different loss with respect to the underlying distribution. So asymptotically, this is what W hat is. And now, to understand whether we get benign overfitting in classification, it's enough to understand whether this kind of weighted squared hinge loss is or isn't a good convex loss surrogate for misclassification error. So again, our goal is to minimize misclassification error. Instead, we get that the W hat that we have minimizes this kind of loss. So this is a convex loss. It's not a misclassification error, but intuitively, in many cases, it would be a reasonably good surrogate because it does encourage the sign of the prediction to align with the sign of the y. So, it's the same reason why we argue that to minimize 0, 1 error, it's reasonable to minimize a convex surrogate classification loss. Okay, so anyway, based on this characterization, we can now, try to analyze various settings. So, the kind of maybe the most basic interesting setting here in the concept of benign overfitting is that we have some kind of label noise, inherent label noise, and we minimize a predictor to get zero training error. So it's overfitting, but when can we still expect benign overfitting to occur? And then we can show, and then it just kind of turns out it just boils down to whether a certain loss function is a good surrogate for misclassification error, depending on the noise level. So we can show things like, for any distribution, you have benign overfitting for some level of noise. You can also talk about mixtures of symmetric distributions, in which case you do get benign overfitting for just about any non-trivial noise level, and you can study other settings as well. Okay. Any questions about this before I move on? Yeah.
So for the classification setting, do you still need some condition on the tail of x d minus k so that you can overfit the noise in this case, or is it different from the regression case?
Yes, so we're still in a setting where you have like k coordinates with some fixed distribution, and then like a tail of, like a long tail of coordinates with a very small variance. So again, we're in the setting which was shown to be necessary for benign overfitting in the context of well-specified linear classification. And that's the main assumption in all of these theorems. Okay. So now I'll switch gears and talk about using implicit bias for a very different purpose in the context of reconstructing training data. This is also, this work is also a little bit more empirical. Okay, so the task that I'm going to talk about is someone gives me a neural network that I know was trained on some training data, and I want to understand whether, given this network, I can reconstruct the data that the network was trained on. So, many people believe that neural networks do memorize the training data in some sense. So we saw in Misha's talk earlier, where we have like these large neural networks with hundreds of billions of parameters and hundreds of billions of training tokens. In some sense, the network has enough capacity to basically memorize the training data, but does it really do it or not? So there were actually a couple of interesting work that showed, at least in some situations, that the network does memorize at least certain data points. So like if you use these GPT-style language models and ask it to complete some sentence and you start it, exactly in a way that corresponds to a certain training data, then at least in some cases, it will kind of complete it to, the training data. So that's like a proof of concept that the model at least memorized that example. So this is kind of nice, but it's also a little bit specific to generative language models. What if we're talking about some other network, some generic network? Does it have this kind of memorization behavior or not? And if it does, can it be recovered? And what we're able to show is that the answer is actually positive. I'll emphasize, at least for relatively simple multi-layer perceptrons, so like fully plain vanilla fully connected neural networks. For more complicated networks, this is still less clear. It's still work in progress. And actually, I'm going to show you how this can be done using the kind of implicit bias characterizations I talked about in the previous part of the talk. And of course, if this is true, then it has, of course, negative potential implications on privacy, because it means that, if the network was trained on sensitive data, at least in principle, it might be possible to extract that data. And as I said earlier, there have been some previous work along these lines, but they were either kind of specific to language models or focused on getting information on single examples. Just find some example from the training data or some representative. But I really want to talk about, extracting entire chunks of the training data. And maybe I should also say that the technique I'm going to talk about is a little bit related to known attacks in the context of federated learning, but it's kind of a different goal. There, it's about getting gradients from the training process of the neural network. And we also do something with gradients, but the input is totally different. In our case, no one gives me gradients. You just get a network that was trained on something. And this is like maybe sneak peek at some of the results. This is the context of examples from CFAR 10, where just given the network, we were able to extract at least some of the images. So at the top you can see the reconstructions, and at the bottom is the kind of the nearest neighbors from the training set. Okay, so how do we do this? So recall that for linear predictors and classification, it's known that with standard gradient methods, you converge to the max margin predictor. Forms such that the margin is at least 1. Now, it turns out that it's possible to generalize this to homogeneous neural networks. So basically networks where you multiply all the parameters by some number, the output gets scaled by some power of that number, in which case you get that, again, with standard gradient methods, you converge to a KKT point of a max margin problem. So your network is now parameterized by some theta, and the theta would be a KKT point of this problem. So again, you minimize the norm of the thetas such that the margin on the example is at least 1. Okay, so KKT point does not necessarily mean that we converge to a global optima of this problem, but intuitively it means that the algorithm is at least trying to optimize this max margin problem. Okay, so how can we use this? So recall that the KKT, so in this context, if theta is a KKT point, it means the following 3 conditions. It means that I can write theta as a linear combination of the gradients at the training examples, at the xi's. Gradient is with respect to theta. It needs to be a feasible solution. The margin is at least 1. You have the condition that the Lagrange multipliers are non-zero only if the points are exactly on the margin. So you get an actual margin of 1. Okay? This is regardless of whether you got to a global optima or not. As long as you get to a KKT point, these conditions hold. Okay, now here's the key idea. Someone gave me a network with trained parameters theta. Maybe the only thing I know about it is that it was trained with some standard gradient procedure. Then I might hope to assume that the network, at least approximately, satisfies these mathematical conditions. So what can we do? I don't know the x's and the y's, but I do know the thetas. So I can try, given these constraints and given theta, to find the x and y's and the Lagrange multipliers that would satisfy these conditions. Now, why would I have any hope of succeeding? At least information theoretically, because when we talk about large-scale neural networks, I have many more parameters than training examples. Then what I have here is essentially a nonlinear system of equations with p equations, one equation for every network parameter, and I have m times d variables. So these are all parametric networks. I can hope that p is larger or even much larger than m times d. Hence, I should have enough information to recover the data given the network parameters. And also, notice that this thing only really allows me to reconstruct inputs on the margin, where the lambda i's are non-zero. And this is also something that we observed empirically. So trying to reconstruct data points through this tends to return examples that are on the margin. Luckily, because the kind of tasks that neural networks are trained on are not very easy, you do tend to get a lot of examples on the margin, so we can extract a lot of training examples this way. Just to go a little bit more into the specific details, so first of all, we don't know M. I'm not assuming I know how many training examples we had. We also don't know what's the distribution of the labels, but it's fine. I can just try to reconstruct a large number of points, so like more than twice the number of training examples. Just assume that the y's are balanced. In this case, I try to reconstruct too many, but then it's like just assuming that their Lagrange multipliers are zero, so it doesn't really affect things. And then the kind of our objective is, so remember, KKT conditions imply that theta should be in the linear span of the gradients, so we can just take the square distance of theta from this. And we also want to encourage the lambdas to be non-negative. And then we just get this kind of non-convex optimization problem that we can optimize with any non-convex method you want, gradient descent or anything else. Maybe surprisingly, it works pretty well. So, again, at least on relatively simple neural networks, we can actually reconstruct a very significant portion of the training examples. So, again, these are like some more examples. This is in the context of MNIST. This is in the context of CFAR on 500 examples. So we definitely don't reconstruct all of the training examples, but a pretty significant chunk. I should also notice that, you need also to discuss about baselines. So, maybe, there aren't really a lot of baselines in the literature that, at least that we could find that we could compare ourselves to, but like maybe one simple suggestion is just look at the weights. So like maybe the first layer weights basically encode various examples, and maybe you can just read off examples from that. So it turns out that the first layer weights do contain some information, but definitely not at the same level as what we can get with our methods. So this is like in the context of CFAR, in the context of MNIST. So, you can get maybe the a couple of examples, but pretty quickly it starts to really degrade. Okay. Okay, how much more time I have? Okay, great. So take maybe 10 more minutes, talk about the last part where again I'm switching gears and talk about implicit bias in the context of adversarial examples. I guess most of you have at least heard about adversarial examples, so it's this pretty universal behavior of modern neural networks that they can get very good test performance, but they also tend to be very, very brittle to adversarial perturbations of the data. So no matter what application you look at, in terms of image recognition, you can take an image of a duck, and the network very confidently predicts it's a duck, then add a very small perturbation to the pixel values at a level that, like, to us, to the human eye, it's not even discernible that some perturbation occurred, but this perturbation makes the network to now equally confidently predict that this is actually a horse. And you see this again and again. You see this in speech recognition, that you slightly change a certain audio signal and it makes the network make horrible mistakes. Also in the context of videos, and of course it has various implications in terms of security and safety, and it's very well studied and empirically verified phenomena. But the question is, okay, it's very ubiquitous, but why is it so ubiquitous? So, some explanations that are easy to rule out. So it's not because these problems don't have a robust classifier. So in context of image recognition, we are a robust classifier. We know that this is a picture of a duck. You slightly change the pixel values. Most people won't change their prediction as a result. You can also argue maybe it's some limitation of expressive power. Maybe neural networks are not able to express robust classifiers. That's also, I think, not very likely because we do train very large, very over-parameterized neural networks. So kind of the main thing remaining is that it has to do with the training of these methods. Then again, somehow the dynamics of the algorithm, the implicit bias of the algorithms that we use, somehow they are biased towards predictors that are sensitive to adversarial examples. So this maybe is more plausible, but the big question here, how do we show this rigorously? So in previous work, kind of the main theoretical results we had was that adversarial perturbations indeed exist, but that was for networks where the weights were chosen at random. There was no training taking place. You'd fix the network architecture, you chose the weights at random, and then you showed that this network had sensitivity to adversarial perturbations. So these are very nice results, but it doesn't necessarily say anything about trained neural networks, which are not, of course, random. So what we're able to show is that, at least for very simple one hidden layer in neural networks, there are data sets where adversarial perturbations, so where the trained networks are provably non-robust to adversarial perturbations. More specifically, there are settings where, on one hand, there exists a robust depth to ReLU network. And on the other hand, any network that gradient methods, and gradient flow might converge to, are non-robust. And they're very non-robust in the sense that a single perturbation applied to any single training example would flip all the labels. And the size of the perturbation is much smaller than the size of the perturbation necessary to flip the predictions of the robust network. Okay, and this is without any assumptions of the network width or the initiation. And it's also something that you can observe, at least in these settings, in practice. Okay. So just to explain how the result works, so again, we recall this implicit bias result for homogeneous neural networks and the convergence to the KKT point. Now, when you look at this, you might think that we should get a robust, so if this was a linear predictor, this max margin problem exactly says that you want the decision boundary as far away from the training examples as possible. So like you try to train a robust classifier. The important observation here is that once you talk about nonlinear predictors, this kind of max margin problem, even if you find the globally optimal solution, it does not correspond to margin maximization in function space. So the kind of prediction function that would result from this is not necessarily one which tries to maximize the decision of the prediction boundary from the training examples. And hence you don't get a robustness. You can also show this in like a simple example. I think I won't go into the details, but again, the point is that unlike in the context of linear predictors, for nonlinear predictors, max margin is not margin maximization. So a little bit more formally, kind of the result is that whenever you have examples where the training data is kind of spread, okay, so like the inner product between the different training examples tends to be small, then for any depth to rel network and any KKT point of the max margin problem, no matter which one, you can find a small perturbation, a vector z, that flips all the labels. And even though this is, in this situation, robust networks do exist. And you can actually extend this a little bit. So here M is the number of training examples. You can actually show that also occurs when the number of when M is just the number of points on the margin. Also, a limitation of this theorem is that you need the ratio between D and M has to be kind of reasonably bounded, but experimentally we can show you really need M to be smaller than D, but actually you get that when you train these neural networks in this kind of setting, then you get this, so like the kind of perturbation predicted by the theorem also fools these networks, even when when the number of training examples is significantly larger than the dimension. And again, you can also see how it does not depend on the width of the network. And there are some interesting open questions here, extending this more rigorously and to other architectures and other data problems. But at least for certain settings, you can show that training neural networks with gradient-based methods really result in non-robust networks. Okay, so I'll wrap up here. So again, I talked about implicit bias in 3 different contexts. I started with context of generalization and benign overfitting. Then I talked about using implicit bias results for data set reconstruction, as well as robustness to adversarial examples. But of course, you can also take this in many other directions. So for example, there has been a line of works on how implicit bias of training algorithms kind of bias ourselves to networks which have low rank, where the weight matrices of the different tend to have a low rank, and we also have some results, recent results on this. Another thing is that many of these results was about convergence to KKT points of a certain max margin optimization problem, but KKT point is not necessarily a global optimum. So, is the bias towards actual margin maximization actually getting to global minimum? And if not, then when yes, when no? And there are many other directions that we and others are currently working on. So I'll stop here and take questions. Thank you very much.
Hi, thank you for the interesting talk. So just a question about the reconstruction. So you train the models like few examples, like 500 examples or something, and then you use the KKT to reconstruct the example. So what happens if you train the model on the full data set and then try to reconstruct just like 10 examples? Do you get some representatives of some clusters in the data or something?
So you get, so you mean like if you run it on the full data set?
So you train the model on the full data set, and then you want to reconstruct just like 10 examples. So do you get like some representative points of some clusters in the data or something?
Well, we do tend to get, sadly no, because we tend to get points which are close to the margin. So like so if you assume that your data is kind of composed in clusters, you actually tend not to get the points that are like at the center of the cluster, but more those on the edges. Again, because the KKT theory tells us that these are the points that would get more representative, like kind of the harder to predict. The network has to kind of work harder to predict correctly on them, so these are the ones that tend to be represented more. Now, it's not that we get like pathological examples, I would say. So, you know, like if you look at the here, for example, you know, we don't get these like, you know, few very weird examples which really don't look like a digit or something. You get reasonable ones, but yeah, geometrically these are the points that are on the margin. So they tend to be like the ones that network finds it harder to classify for some reason.
I see. Thanks.